All right, welcome back everyone. So hopefully you're still following along with your stack of loose sheet of paper, and because this is the only way to do well in this course again. So don't forget, whenever I start writing on board, start copying things on your piece of paper so that you can go back to the lecture notes after a while and compare the printed lecture notes to your handwritten notes that you took during the lectures. Okay, just a quick reminder for that. So on today's agenda, what we have is that we'll first derive, I would say, the second most useful equation in this course. The first one was a two-body equation of motion. The second one will be the orbit equation. And then after that, we'll review Kepler's laws. There are three of those, and see how they can provide with some interesting facts about orbital motion. All right? So in 2.1.3, again, the first thing we're going to do is to derive the so-called orbit equation. So to do this, I'm going to start off by remembering that the eccentricity vector from last time was shown to be equal to the velocity vector cross product of the specific orbital angular momentum vector h over mu of the primary body minus the position vector over the distance r. So as a first step in the development, what I'm going to do is that I'm going to take the dot product of both sides of that equation with the position vector r, like this. Dot product, like that. Okay? As a starting point. So here we're going to leave the left-hand side as it is. So position vector dot product of the eccentricity vector equal to, here the first thing we'll do is that we are going to distribute the position vector inside the brackets, and then just write that this is position dot product velocity cross product angular momentum over mu, all this minus r dot product with itself over distance between m1 and m2. Okay, so it looks like a mess, so we're going to clean it up a little bit, and the first step in doing so is to focus our attention on the numerator here. Okay, so we have a dot product of two vectors followed immediately by a cross product. Turns out in chapter 1 there's a nice little identity that allows us to write that slightly differently. So specifically, I am looking at identity. Do I have? Yeah, 1.22. Okay, I'm going to say using equation 1.22, which is one of the identities. Identities discussed in chapter 1. I'm going to rewrite this. So we can write that r dot product v cross product h is equivalent to r cross v and then dot product h. Turns out that doing so is very convenient for us because we know very well that position vector cross product of the velocity vector is equal to the orbit angular momentum vector h. And thus we are left with h dot product with itself. Now you know very well that this is just equal to the norm of h squared, and the norm of h here is denoted by h simply, so h squared. All right, so this allows us to write that equation as h squared over mu minus, look at what we have here. We have the dot product of the position vector with itself, so that would be r squared divided by r, so just minus r, like this. And already we are pretty much done because the last thing we need to do in order to derive the orbit equation is to shift our attention to the left-hand side of that original equation. So for that, we have to remember the definition of the dot product of any two vectors. And the definition told us in chapter 1 that we need to take the magnitude or the norm of the first vector times the magnitude of the second one times cos of the angle between those two vectors. So let's do it. So the norm of r vector is r, which is the distance in terms of length between m1 and m2. Same for e. We're going to denote the magnitude of the specific vector, which is the eccentricity vector that again always points in the direction of the perigee, as simply being e. So re, and then cos of the angle between those two vectors. We shall denote that angle by theta. Okay? And I'll come back to this new variable in a moment. But let's just finish up solving for the orbit equation. So Re cos theta equal to h squared over mu minus r. So from that point on, it's good to realize that the orbit equation is actually an equation that allows us to calculate the distance between m2 and m1, or the distance between the spacecraft and the primary body, or the planet, as function of the other variable. So because of this, the trick here is simply to solve that equation for r. So I'm going to pull this r on this left-hand side, and I'm going to write that r times 1 plus e cos theta is equal to h squared over mu. All I did was to pull this r on this side and solve for it, and I got this equation. So next, I'm going to finally solve for r on its own by saying that r is equal to h squared divided by mu. All of this divided by 1 plus e cos theta. And ladies and gentlemen, you did it, okay? You solved for the orbit equation. Yes, well done. That is great because this is, again, the second most powerful equation in this course after the two-body equation of motion, which was equal to, yes, exactly, r vector double dot is equal to minus mu over r vector divided by the distance q, r cubed, okay? So this is great because now it allows us to solve for the distance between m2 and m1. So if you have an orbit, yeah. Note to myself, do not draw orbits in black, otherwise they don't show up. So red is much better. And a couple of times, like that. So you know that you have M1, the planet, M2, the spacecraft orbiting around. So as you know by now, the distance between M1 and M2 varies as the spacecraft orbits around M1. And that distance reaches a minimum at the perigee here and reaches a maximum at the apogee of the orbit on the other side here. Well, a couple of things to note here is that to calculate the magnitude or the distance between M1 and the spacecraft at any point along the orbit, through the use of that equation, well, all we need is to know h, which is a constant for a given orbit. Remember, that was our first fundamental integral of the two-body problem. So h is constant for a given orbit. Mu's are a gravitational parameter for the primary body M1. E is the magnitude or the norm of the eccentricity vector that always points in the same direction. So E vector was shown to be constant. That was our third fundamental integral of the two-body motion. So the norm of it is also a constant. Essentially, in that entire equation, everything is constant, but the true anomaly on the right-hand side. And obviously, R varies tremendously throughout the orbit. So as long as you know at which point you are interested at calculating the distance R, well, all you need to do that is to solve or to substitute theta for the value of interest, and boom, you're going to get R, okay? So what is this angle? Well, again, we had, if you remember from before, the equation was something like that. So that was our left-hand side of that equation. Our vector dot product eccentricity vector, which we had to replace through the definition of the dot product, our E cos theta. So this theta is just the angle between our position vector R and the eccentricity vector. Now, because the eccentricity vector is always constant, it means that theta is actually the angle between where the spacecraft is currently, say the spacecraft happens to be here, and that fixed reference, which is the line that goes through the perigee from M1 along the eccentricity vector. So this is our true anomaly, okay? Because this angle has a name, I just said it. This is the true anomaly, okay? So if you say, okay, I'd like to know the distance between the planet and the spacecraft when the angle between eccentricity vector and the position vector is 280 degrees. Well, that's easy. Just plug 280 degrees in radians, or in degrees, it doesn't matter really, because it's close out. So plug that into the equation here, and you're going to calculate directly the distance between M1 and that specific point along the orbit. Okay? And this is why this equation is so powerful. It's really a plug-and-play equation that we're going to use tremendously in this course. Again, this is known as the orbit equation. Okay? Something else to note here is that the ratio you have on the numerator of the orbit equation is actually a constant, right? H squared is constant, mu is constant. So for ease of derivation in future, we'll simply now replace the ratio of those two constants by a single constant that we shall denote with P, okay? Over 1 plus E cos theta, where we've just used the fact that P is equal by definition to H squared over mu, like that. And interestingly enough, if you go back to the orbit, P has a geometrical meaning. Okay, so again, M1 here, which is the planet. P happens to be, if you just look at the equation, happens to be the distance between M1 and M2 whenever the true anomaly theta is equal to pi over 2, or 90 degrees. So that means that R is equal to something else, and boom, whenever the angle between eccentricity vector and the position vector is exactly 90 degrees, while that distance, or the norm of your position vector R, becomes exactly equal to P. Okay, so P is that distance from M1 straight up along the orbit. And same thing on the other side, because the orbit is symmetrical about this line here, okay? So this dimension here is r equal p as well, whenever the angle is pi over 2 or 3 pi over 2. All right? So that concludes 2.1.3. So another very interesting fact about the orbit equation is that it actually describes what's known as a conic section. So that's what we're going to have a look at in 2.2. Conic sections. Okay? I'm just going to, because we're going to refer to that equation quite a bit, I'll just write it over here. 1 plus e cos theta is our orbit equation. So that equation is actually a polar equation in terms of r and theta that describes any kind of conic sections, and the difference between the conic sections you obtain in polar coordinate is only a function of eccentricity, essentially. Okay? So based on the eccentricity value, in other words, we're going to generate a different conic section. The most generic one is known as an ellipse, and we'll see that under specific cases. We can also generate a circular conic section, or a parabolic conic section, or a hyperbolic conic section too. Okay? So you have figure 2.2. So let me attempt to draw this. Essentially, you can have 4 different conic sections. Can be generated by just changing the value of the single parameter, which is the eccentricity value. Okay? So what I'm drawing are geometrical 2-dimensional shapes, and specifically double cones. It's as if you had one cone here sitting on top of another cone there. Just like this, okay? And I'm gonna highlight the fact that the difference only comes from the eccentricity. Only I am going to highlight this parameter in red, okay? So if you have the eccentricity value, which lies between 0 and 1, like that, you are going to generate an ellipse, and that is when you intersect this double cone arrangement with a plane at a random angle, okay? So if you cut this double plane, or this double cone 3D shape with a plane at some random angle, the shape you're going to generate on the plane is actually an ellipse. Okay? That's whenever the eccentricity value lies between 0 and 1. If the eccentricity happens to be exactly equal to 0, that means that this plane intersects double cone arrangement exactly parallel with the bottom and with the top, in which case the shape or the curve you're going to generate on the plane will be a circle. Ellipse. circle. Now, if the eccentricity is exactly equal to 1, you are going to generate a parabola. And that is whenever the plane of intersection with the cone lies parallel with those two slopes, either that one or that one. So let me try to draw it properly. If you have a plane that cuts through like this, the shape you're going to see on the plane, which will be the intersection of the double cone and that plane, will be a parabola, which should look something like this. Okay? Yes, makes sense. And whenever the eccentricity is larger than 1, you're going to generate a hyperbola. And that will be whenever the plane with which you cut through the double cone lies vertically. In which case you're going to generate two halves, which would look something like this. Two halves of an open curve, okay? So one thing to notice is that if the eccentricity is between 0 and 1, either one of those two cases, what you get is a closed orbit, okay? But if the eccentricity gets equal to 1 or even larger than 1, what you get is an open-ended trajectory as opposed to a closed orbit. Those type of trajectories about the primary attracting body are useful especially for interplanetary travel when you're trying to escape the gravitational field of the planet. If the objective is to stay on orbit around the planet, you better stick with those two first cases because those are closed curves around the planet which will lie in the middle. Okay? So all this to say that only by varying the eccentricity value, by varying this parameter in the orbit equation, we can easily generate different types of orbits. Either an elliptical orbit, a circular orbit, a parabolic trajectory, or a hyperbolic trajectory. Note that those two aren't called technically orbits because they are open-ended, okay? Open-ended, whereas those two are orbits because they're closed curves. All right, so we're going to shift our attention on the first two cases only because those are the most useful curves or trajectories or orbits in our case, okay? So let's first look at the most generic type of orbit we're going to play with throughout the course, which is the elliptical orbit. And I will be in section 2.2.1. 2.2.1. Have a look at elliptical orbits that are generated whenever the eccentricity value or the norm of the eccentricity vector is larger than 0 but smaller than 1. So the first thing to talk about is the mathematical definition of an ellipse. So math definition, and that is that I'm going to draw it graphically instead of writing it in words. But if you have an ellipse in red, sorry, otherwise you don't see anything. An orbit in red like this. If you go, an ellipse, by the way, has two foci, one here, one over there. It has an origin right in the middle. Yeah, okay. So the mathematical definition says that if you start at one of the two foci and you go up to any point on the ellipse and you go back down the other focus, then the sum of these two sides, so that one plus that one, will always be equal to 2a, okay? And just say side 1, side 2, which aren't necessarily equal to each other because it could go from here all the way to here, and then from here down to the other focus. We call it side 1, side 2 there, such that side 1 plus side number 2 will always be equal to 2 times a. Now, what is a? Well, a happens to be semi-major axis of an ellipse. So semi-major axis means that you go from the center of the ellipse all the way to the end of either this side or that side, okay? Either this is A from the center to here, and this is A again from the center to this side of the ellipse. Semi-major axis, meaning that this is half of the major axis, which is the longest side of the ellipse. So that is the mathematical definition, that side 1 plus side 2 is always equal to 2a. Okay? Also, in this figure, now that we know what a represents, we can also look at the semi-minor axis. Semi-minor axis, which is denoted by B, and graphically B is again from the center of the ellipse, but this time going up or going down all the way to the bottom. So this is B, such that the short side here, which is twice the semi-minor axis, is simply the minor axis. So minor axis, the short side, major axis, the long side, semi-major axis is just half of the long side, and that is A. Semi-minor axis is half of the short side, and this is B. Okay? Also, another dimension to add to this drawing is to go from the center to either foci, and this is denoted by C on either side. From the center to this focus 2, C again. I'm not even sure if C has a particular name, whereas A is semi-major axis, B is semi-minor axis, but for C, I don't know. Let's just call it C. Okay, so with that, well, just before, the eccentricity that we've talked about can also be defined from a geometrical point of view. Eccentricity, which is E, from a geometrical point of view, yes, thank you. It's getting late here. We can say that this is equal to the ratio of C over A. So right away, just by looking at a generic ellipse, you can already say that, yes, it makes sense that the eccentricity has to be larger than 0, yet smaller than 1. Because this side, from the origin to a focus, will always be smaller than the origin all the way to the end here. Okay? Okay, so let me redraw this cluttered figure here with just the elements I want to keep deriving some useful equations that are related to elliptical orbits, okay? Because this is what this subsection is about, is to talk about elliptical orbits. And in following, we'll derive a bunch of handful relationships that will be much useful down the road when we get to analyze orbital motion for elliptical orbits. So, we have an ellipse, red. We have our center. We have one focus here. This side has a length of C. From the center all the way up, this side has a length of B, our semi-minor axis. And this side here turns out will be of a length of A, semi-major axis. Why is that? Well, that is straight from the mathematical definition of an ellipse that said that if you go from one focus up and all the way down to the other focal point, this plus this will always be equal to 2A. Well, if the point at which you intersect the orbit is chosen 90 degrees from the major dimension of the ellipse here, so straight up, so in other words, exactly between both foci, well, it means that this has to be A, and that one has to be A, such that that plus that will end up being 2A, okay? So this is a particular situation where the point of interest, when you apply the mathematical definition of an ellipse, is chosen right here, such that side 1 is equal to side 2. Okay, well then we can say that A squared is equal to B squared plus C squared, just from the geometry of the problem here. Okay? But we know from before that the eccentricity was defined from a geometrical perspective as being the ratio of C over the semi-minor axis, or semi-major axis A, which means that we could rewrite C as being eccentricity times semi-major axis. And thus we could rewrite that other equation that we've just derived geometrically by saying that A squared is equal to B squared plus C squared, but C is equal to EA. And therefore, this is plus E squared A squared. And based on that very simple equation, we could solve it for B. And B will be equal to A squared minus A squared E squared. You can factor out the A squared on the right-hand side of that equation. Write 1 minus E squared is equal to B squared on that side, such that you get B equal to A square root of 1 minus e squared. And that is a useful expression that you can use whenever you are dealing with an elliptical orbit. Okay, so that is how to find the size of the semi-minor axis B given the semi-major axis A and the eccentricity value E. Okay, very useful. Well, let's keep deriving other useful relationships like that that are applicable to elliptical orbits. The second one is that, I'm going to write it, it can be shown, meaning that I'm not going to derive it for you because I'm pretty sure that this is one of my problems in the problem sets where I asked you to derive that expression. So I'm just going to give you the relationship here, and that is that P, which again is the dimension from one focus to all the way up along the orbit, and that dimension is P. So P is actually related to the semi-major axis A and the eccentricity value in that fashion. So P is equal to A times 1 minus E squared. Another very useful relationship to keep in your back pocket to analyze elliptical orbital motion. All right, so that means that if you go back to the orbit equation, which from before was R equal to P over 1 plus E cos theta, you could rewrite it by making use of this relationship here as R equal to A times 1 minus E squared over 1 plus E cos the true anomaly. From that other version, if you will, of the orbit equation, and also it's handy to have this one ready to go whenever you need it, you can tell that the distance between M1 and M2 will reach a minimum whenever the true anomaly angle here is equal to 0. Because if true anomaly reaches 0, then cos of 0 is 1, then you maximize the denominator, and therefore you minimize the value of R. So I'm going to say R reaches a minimum minimum when the true anomaly angle theta is equal to 0 degree or radian. Okay? In which case, R will be equal to A times 1 minus E squared over 1 plus E. Or alternatively, P over 1 plus E. Yep. Okay? And whenever that situation happens, we'll refer to this specific distance as RP, because we are now at the perigee of the orbit, as we've discussed in the previous lecture, right? If you're not too sure, let me draw another orbit real quick. We have an orbit, the planet that sits directly on one of the foci of the orbit, M1. This point here is the closest to M1, and therefore this is known as the perigee. And the distance between M1 and that perigee is denoted as RP, and was mathematically obtained whenever the true anomaly was equal to 0. And that makes a lot of sense from what you knew already, right? Because true anomaly is the angle between the eccentricity vector and the position vector. So starting from 0 to pi radian, 3, pi over 2, then 0 again, and it circles back like this. So when the angle is 0, it means that you are sitting right there at the perigee, and that is indeed the point of minimum distance along the orbit. Okay, so this relationship is also good to have in your back pocket. And similarly, we're going to say that that orbit equation, or that one, doesn't matter, we'll see R reaching a maximum whenever the true anomaly will be equal to pi radian. Or in other words, whenever R vector is directly over there at the apogee of the orbit. When that happens, you're going to get R equal to A times 1 minus E squared over 1 minus E. Or alternatively, simply P over 1 minus E. Because in this case, you are minimizing the denominator, and therefore you are maximizing the distance R. And whenever that happens, we're talking about a specific point along the orbit, and that is the apogee, and therefore that specific distance here is denoted R subscript A. So another very useful relationship to apply whenever you are analyzing elliptical orbits. The last thing to do, and it's one of the problems in the problem set in chapter 2, is to relate those two relationships together and combine them together. Okay? So, I'm going to leave the details up to you because it's one of the questions in the problem set, but it can be shown, and you'll have to show that R, while semi-major axis A, is actually the mean distance between the apogee and the perigee, just like that. And that can be shown just by playing around with those two equations really easily. The second thing that can emerge from combining those two equations is that the eccentricity could be obtained by simply as a function of RA and RP. Like that. Okay? Again, just two useful relationships that are good to have ready to go whenever you have to derive equations specifically for the case where you have an elliptical orbit. All right, so that was subsection 2.2.1, elliptical orbit, which is the most generic conic section that arises through the orbit equation, which describes, as I told you earlier, any conic section. So the deciding factor about which conic section is going to be generated from the orbit equation is just by selecting the eccentricity value. If it's equal to 0, this is a perfectly circular orbit. If it is larger than 0, yet smaller than 1, then you're going to generate the elliptical orbit that was just analyzed. So let's have a look at the second most useful type of orbits. And then these are circular orbits. The easiest way to think about a circle is that a circle is just a specific case of an ellipse, and that happens whenever the eccentricity is equal to 0. In that case, the conic section will look like a perfect circle, like this, right around M1, which is dead center. There are no foci. There's only one origin, which is the center, and this is where the primary body sits. Okay? So that means that there's no semi-minor, semi-major axis in that case. All we have is R, which is a constant. So i.e. R is not a nonlinear function of the true anomaly anymore. Okay? And, well, you could say that that constant R is actually always equal to P as well, because from before, P was a distance between M1 straight up whenever we intersect the orbit, and that dimension is P. Okay? That's all there is to say about circular orbits. Again, just a very specific case of an ellipse, which happens whenever eccentricity is perfectly equal to 0. Now, in practice, that type of orbit doesn't exist because there's no way that you could generate practically an orbit that maintains its eccentricity exactly equal to 0. I mean, in practice, you could go with very low eccentricity values, like 10 to the -6, and we would say that this is a circular orbit for all practical purposes, but in theory, a circular orbit is very, very difficult to obtain, if not impossible, okay? Because of that exactly equal sign right there. Because you could have the eccentricity value that would be equal to 0 at one time, but then 2 seconds later, drag slows you down, and then the eccentricity decreases or increases based on solar radiation pressure or whatever is happening on orbit. Okay? But this is an interesting situation to look at nonetheless. Okay, the last thing on the plate for today is to look at Kepler's 3 laws and see how we can derive some additional relationships that are useful for orbital motions. All right? So Kepler's laws in 2.3. The first law is, I'm going to give it to you for completeness, but honestly, it's not useful at all for us. It just says that the orbits of all planets around the sun are elliptical, i.e. the eccentricity value is equal to larger than 0 but less than 1. Larger than 0, less than 1, because they are any circular orbits when you talk about planets orbiting the sun. Okay. By the way, Kepler made all of his observations based on planets orbiting our solar system, our sun. Back then, there weren't any man-made satellites, spacecraft, but those laws could still be applicable to spacecraft orbiting a planet. Okay, so that just says that if the eccentricity lies between 0 and 1, well, you're going to generate an ellipse. Okay, and that's why I say that the first one isn't very useful to us. We already knew that elliptical orbits is with that kind of eccentricity values. Now, the second one, by the way, that was known as the law of orbits. Second one, which is very interesting for us, it says that the position vector from the sun to a planet sweeps equal area and equal time. This is known as the law of areas. The position vector from the sun to a planet sweeps equal area and equal time, and that is also applicable to the position vector from a planet to a spacecraft. This is our R vector in our case, sweeps equal area and equal time. So let's first derive that, or let's prove that law ourselves, and then we'll see the implications of that. And then we'll have a look at the third one, and we'll call it today. All right, so to demonstrate Kepler's second law, we will consider a very small area that is being swept by our position vector on orbit. So if this is M1, say this is our perigee, eccentricity vector, orbit, position vector at some given time. Then we're going to say that the area being swept is considered to be very small to begin with. So we could pretend that this is a zoom in view. So this is our delta A essentially, whatever lies here. Okay? And that area is being generated by or through a very small true anomaly increment. All right, so essentially what you have, if you want to look at this triangle, is that you have a very small angle here that generates an infinitesimal area, delta A, like that, okay? And to calculate that, well, because the area is so small, we'll pretend that the arc of the orbit here matches the side of this triangle here. Okay, this is an approximation, but because it is so small, that works out pretty well. So we're going to say then that delta A, that small area being swept by our position vector in this short amount of time through a short or small true anomaly angle, will be equal to 1/2 times the base of our triangle, which is R, times the height of our triangle, which is here. And this can be approximated to be simply R times delta theta, which is the area of a triangle, essentially, small triangle, okay? Like that. or in other words, 1/2 r squared delta theta is our small area being swept in a small time step. Next up, we'll have to recall the definition of a derivative applied to a generic variable, say x here. So dx dt is actually the limit of delta t towards 0 of delta x over delta t. This is the mathematical definition of a derivative. Dx dt, the limit of delta t being very low, of d delta x over delta t. Which means that if you are interested in looking at the rate of change in your small area, dA dt, because again, Kepler's second law deals with small area in small amount of time and equal area in equal amount of time. So that's why we have to invoke time here, and I'm going to do that through the derivative. So we're going to say that this is limit of delta t towards 0 of what? Well, delta A over delta t. So again, limit delta t towards 0. What is our delta A? Our delta A is 1/2 r squared delta theta over delta t. Not dt, but delta t. Like that. Now, this is not affected by the limit of delta t towards 0. Hopefully you'll agree. So we could rewrite 1/2 r squared limit of delta t towards 0 of delta theta delta t, and surprise, surprise, what do you get here? You get the definition of a time derivative, right? Applied to the true anomaly as opposed to some generic variable here that we have. So we're going to rewrite that dA dt is 1/2 r squared d theta dt, or simply 1/2 r squared theta dot. How does that help us figuring out Kepler's second law, or proving that he was right? Well, it can be shown. I'm not going to do it for you. You can do it on your own. It can be shown that h, the specific orbital angular momentum that we talked about, can also be calculated as r squared theta dot. Oh, it's very useful because look at what we have here. Then we can say that the rate of change in this small area, dA, is actually equal to 1/2 times h, which means that this is indeed a constant. Yes, you did it. Well, we did it. All right? So we just proven Kepler's second law, or in other words, equal area in equal time. So the ratio of dA dt is actually constant throughout a complete orbit. So what does that imply is the following. Orbits in red. You have an elliptical orbit. Hopefully it's big enough. you have M1 at one of the two foci. If you look at an area being swept an X amount of time by the position vector, and you call it A1, and if you take the exact same amount of time, but near the apogee, and call the area being swept by the position vector in that amount of time, call it A2, it means that if we want A1 equal to A2 in equal time, obviously, right? So this is, pretend this is 5 seconds here. This is the area you get. In 5 seconds over there, you sweep out A2. Well, if you want A1 to A2, that means that the position vector better speeds up here, such that in 5 seconds you cover a greater amount of true anomaly than you would in 5 seconds near the apogee. Otherwise, this wouldn't be large enough to be equal to A2. And this is another explanation as to why spacecraft always travel faster near the perigee than they do near the apogee. And we had already demonstrated that through the conservation of specific orbital energy as our the second fundamental integral. That was the implication. So Kepler's second law also has the same implication here. Okay? All right. The last thing we'll do today is to look at Kepler's third law. Which says that the square of the orbital period is proportional to the cube of the semi-major axis. And this is known as the law of periods. So as we did for the second law, the objective here is to first make sure that Kepler was right. So we're going to demonstrate Kepler's third law and see the implication on orbital motion. So to demonstrate that, it's not that difficult because all we have to do is to integrate from 0 to 1 orbital period, where, by the way, 1 orbital period refers to the time it takes to complete 1 revolution of our spacecraft around M1 or around a planet. So we're going to integrate time from 0 to 1 orbital period, which from now on will be denoted by capital T, of the rate of change in area being swept by our vector dt like that. And if we do this integral over 1 orbital period, we shall get the complete area of our orbit. Okay? Now, good news is that this was actually a constant from before. Kepler's second law told us that that was actually constant and equal to h over 2. Okay, so then we can come back here and say that the area is equal simply to h over 2 times the orbital period. Well, we also know from a geometrical point of view that the area of an ellipse is pi times semi-major axis times semi-minor axis, right? grade 2. Maybe grade 1. I'm not sure. Anyway, kidding. So if that is the case, then we should be able to equate those two areas and say, so A equal A, or pi AB equal to H over 2 times T. B. We know how to express B in terms of the semi-major axis, don't we? As we just saw in the previous subsection that we had a relationship to do so. And that relationship was B equal to square root of 1 minus E squared from the bracket times A. So let's replace B with that. So that we end up with pi A squared, because A, square root of 1 minus E squared equal to H over 2 times 1 orbital period. And then we're going to solve that expression for the orbital period T and see what we end up with. Because again, the objective is to demonstrate that the square of the orbital period, which is T, should be proportional to the cube on the semi-major axis. So let's see if this is indeed what we get. So T, orbital period, will be equal to 2 pi A squared, square root of 1 minus E squared over H. We don't see that relationship yet, right? Because if we were to take the square on that side, we get square of the orbital period proportional to semi-major axis to the power 4. That's not exactly what we want. So it means that A is probably buried also within this variable, which is the orbital angular momentum H. So we have to express now H as a function of the semi-major axis, because otherwise we won't get Kepler's third law properly. So let's first start off by saying that P from before was equal to H squared over mu. But also we had obtained another expression for P, which was equal A times 1 minus E squared. So two expressions for P in the elliptical orbit subsection. So if we equate those two equivalent relationships, we'll end up with H squared over mu equal to A times 1 minus E squared. Or in other words, that H is equal to A times mu times 1 minus E squared, and then square root of all that. That is quite convenient, because now I can go back to that expression with the orbital period and substitute the denominator for what we just found, which is mu A times 1 minus E squared. I'm going to distribute my square root on both terms, so that we can now easily see that we can cancel this on the denominator with that, this on the numerator with this term on the denominator. And then we write 2 pi A squared. This cancels out with that over square root of mu square root of A. Or in other words, 2 pi over square root of mu and square root of A cubed. And that is equal to the orbital period. Ha! We're there. Okay? Because now if you square both sides of that equation, you're going to get the square of the orbital period equal to 4 pi squared over mu times a cube. Oh my gosh. You are so brilliant. We are brilliant as a group because we've just demonstrated Kepler's third law. And that is that the square of the orbital period is indeed proportional through this factor, the cube of the of the semi-major axis. Oh my gosh. Boom, boom. Brilliant. All right. The implication, as usual, I tried to relate whatever theoretical results we obtained to the practical implication on orbital motion as much as I can. And in this case, it's very straightforward. It just means that the larger the orbit, or the larger the semi-major axis, which is a dimension of the ellipse, right? So the larger the ellipse, the larger the semi-major axis, and then the larger the orbital period. All this to say that the bigger the ellipse is, the longer it's going to take for the spacecraft to complete one revolution. And this is rocket science. All right? So, the larger the ellipse, the longer it takes to complete one orbit or one revolution. Okay? Nice. Now, the very last thing is that related to this is the notion of mean orbital motion. So the mean orbital motion is actually a parameter very useful in orbital mechanics, denoted by m. So this is the mean orbital motion. And this one is obtained from the orbital period as simply 2 pi over the orbital period. All right? Or, using this expression, you could rewrite it as simply, because now take the square root on both sides, you're going to get the 2 pi's canceling out, and you'll be left with square root of mu over a cube, which is a constant, and that is just the mean angular velocity, if you will, that the position vector sweeps out the complete orbit. Okay? Units are radians per second. So if it takes 6,000 seconds to complete one orbital period, then the mean orbital rate would be 2 pi radians over 6,000 seconds, and that'll give you constant mean rate at which the position vector sweeps out throughout the orbit. Although in practice, as you know by now, the orbital position does not sweep out the orbit at a constant rate because it goes faster near the perigee and slower near the apogee, speeds up, slows down, speeds up, slows down, but yet the mean of this rotational motion of the position vector throughout an orbit is quantified through this parameter. Okay? I think that's enough for today. I'm going to stop here. So as usual, I hope you enjoyed. Hope you learned more great stuff about orbital motion. And I'll see you next time, guys. See ya.